Stellar. Our project is a dual-axis sun tracking solar panel.
My name is Matthew Diaz. I'm a computer engineer, and I'm the software lead of this project.
My name is Peter Marjanovic. I'm also a computer engineer and the software aspect as well.
I'm Nick Sorgleski. I'm the team leader and also hardware lead.
My name is John Stefano, electrical engineering and hardware lead.
So the motivation for this project, as you can see by this picture, is basically in rural areas where they're so far out from the grid and stuff like that, they have to have a way to power their homes and their lifestyles. So we created an independent source of energy, well, not created, but innovative source of energy with a solar tracker that tracks the sun based on our algorithm, so that it would improve efficiency and make it reliable, make it independent of other stuff like the grid, and just make it reliable upon the constant sun as a source of energy.
Right, so other related products that we've searched for and looked at are this right here is a product from a company called Sol Systems, and they have a single-axis solar tracker in their for the product, and basically it's based off of like a one-motor system where it's only able to track from the sun's movement from east to west. So it has one motor, and it bases off the rising and setting of the sun. But we aim to create a dual-axis system where it has a kind of more free range of motion and have the solar panel like accommodate for any kind of movement of the sun, whether it's from east to west or any kind of shifts over the horizon. So these single-axis trackers are very well, and they're obviously more efficient than any fixed solar panels. So, but these are kind of more aimed for like large-scale use and like huge solar farms where they have like thousands of solar panels like outputting daily for energy. And right here is just included like just a graph of the power output compared to the time for like a day of a solar panel. So the black line there is the fixed, basically just a basic solar panel where you can fix it on your roof or wherever, and it's a fixed tilt, and you can see that the power output is more of a curvature, and it has like it compares from like sunrise and it goes over to sunset. The single axis, which was the previous product we showed, which from a different company where they had, is the gray line, and has a better curve like towards the beginning of the sunrise to the sunset. But as you can see, our orange line is our dual axis, which we're trying to recreate, and has a very large range for power output. So we're trying to create a dual axis tracking system, and there's a project called Project Sunshine that was previously created in another Capstone group a couple years back, and both of our goals are to create increased efficiency of solar panels, and our design kind of stands out from theirs because we're able to have our goal is to have more of like a residential, like a personal aspect to our solar panels. So instead of having to nowadays, like when you're buying like personal use solar panels where they're fixed, you have to buy multiple of them, and they might not have the best energy output for your home or wherever you want to put it. So we aim to have our system be custom to the user and be able to integrate into the Internet of Things for any user network.
Okay, so for our project, the three main aspects we looked at were the cost, design, and efficiency. So we looked at in a mobile panel, a single axis panel, and a dual axis panel. We found that the dual axis, while it does cost more initially to set up, in the long run, it's better in design and efficiency because of the outputs like we've seen in the graph. And one of the statistics we found is that the dual axis trackers are about 45% more efficient than fixed roof mounts and about 30% more than fixed ground mounts. Project summary, so ours, like Peter said, is geared more towards like residential areas or smaller spaces because they don't have much space to put many solar panels, maybe only one like in our case. So our system would be a solar panel that tracks the sun based on its location. So we plan to do that by having a series of motors connected to a microcontroller, which gets the sun's location information from Bluetooth, like a Bluetooth module, which is connected to an application. And then also, we plan on integrating a series of, like an arrangement of photoresistors that are able to like pinpoint the exact location of like the source of the light. So it's kind of like a backup or like a fail-safe for the motors to move to actually be in the right position to get the most like sun hitting it. Then the needs identification. So solar energy is like a rapidly developing field, like being widely researched. So the need is definitely there for our product, and like as I said before, the main like component of our idea is more residential areas, like smaller spaces. Like the dual axis system doesn't really have much of a greater impact for these big companies that are able to have multiple different solar panels within their land, like in the space that they have. So ours is more for smaller cases.
So for marketing requirements, this technology must increase the efficiency of the solar panels and in turn help to lower the cost of electricity for the customer. Like Peter said, we're going to attack more of a residential market rather than commercial, so for daily, dollar average, New York in our case, we were able to run numbers from it, which we'll get to later. So the system must be reasonably sized to allow for maximum flexibility for the customer to install the device wherever desired and cause minimal intrusion in the space provided. So typically, we're going to aim to place them on, roofs of homes, try to get the most sunlight, or perhaps, like a backyard space or some property towards the side that the person owns. Anything that would allow for the most sunlight, taking into account trees, fences, anything like that to create a blockage. The system must be durable and reliable to reduce the amount of maintenance and worry. So this would be, the weather, rain, snow, or anything like that could actually affect the physical panel. Just some requirements that we were able to come up with. So the marketing requirements that we broke up into engineering requirements and justification. So for example, if it came down to energy efficiency and reliability, you have to take into account the system should be able to power itself and function consistently to run throughout, let's just say for 1 year before the actual piece would be maintenance. Justifications such as how this should allow for the system to be self-sustaining and not have to rely on outside power for functionality. And for anything more basic when it comes to just reliability, the system should function through all seasons, like I said before, all weather conditions, rain, snow, etc., hail. And this should cut back the need for constant maintenance and replacement of the system. So when it comes to our trade-offs, when we first came up with the design, there's some things that we have to take into account. If we want to bring up how much energy we're going to have to save, we're going to have to decrease the size of our actual physical piece, which would increase reliability. We're going to increase the size of the actual device. It may decrease how reliable it's going to sustain throughout a year or 10 years or something like that.
So this is the system description of the product that we're making. These are the three individual modules, starting with the Solar Track, which is the smartphone application that will monitor the solar panel and basically output to the user the usage and the position, the output, such as how efficient the solar panel is, how much energy is gathering per a certain amount of time in the sun, at what position it's facing, and at what time of day is the solar panel facing that way. That will relay that information obtained from the solar panel via Bluetooth connection. The integrated circuit, we're using an AT Mega 328 microcontroller chip, and we connected a Bluetooth module via serial pin to then connect to the smartphone application that we are in the process of implementing. And the microcontroller is going to move the solar panel via the dual hydraulic motors that my colleagues were talking about earlier to construct our dual access solar panel. The related theory, so basically we didn't implement any mathematical equations in this slide because the implementation that we have currently is really simple and conceptually easy to grasp. So basically, we have we have a photo resistor on each corner of the board, and it's basically averaging out each pair of resistors based on the sun intensity that it's gathering. So basically, if the sun is hitting, so let's say this is the solar panel, if the sun is hitting these two photoresistors, the intensity is going to be greater than the average of those two. So it's going to then shift to this side and grab the sun completely from this angle. So basically, that's why we didn't put anything, because it's just an average formula that we were going to put on here, and that's redundant because, you know, college students.
So basically, this is the data flow diagram of our whole system. So you can kind of see the two components we have working together here. So basically, we have our phone application where it's going to have the sun's location. It's going to have an algorithm for that. There's going to be an algorithm inside of the board itself controlling the solar panel. So it's going to obtain the location of the sun, and it's going to send the data over to through the Bluetooth relay to the microcontroller itself, and that's going to control the solar panel. So that data is going to be stored, and while that's happening, there's going to be the sensors that we were talking about on our solar panel, and that's going to be the sensor data is going to be stored in the memory, and then those signals are going to be compared, like the signals when he was talking about the averaging, they're going to be compared, and then it's going to make an assumption. So if it is facing the sun, then nothing's going to happen. It's perfectly fine. It's facing the sun, it's having the maximum energy output. But if it is not, then it's going to have it's going to compute the position adjustments based off of the sun location, the sun geolocation, and it's going to make those positions, compute them, and then create them into a tangible number so that the signals can be sent to the motor and adjust based off of that.
So this is the solar track application that will be monitoring all of this. As what I explained earlier, the application connects to a geographical server via the network provider, because it's more reliable than a Wi-Fi, because the lag is, I think it was 10 minutes when we were trying it out with a Wi-Fi server, and with a network provider, the lag went down to around 10 seconds. So that's why we switched to the network provider to record the data and then send it to the Bluetooth module, and then through the Bluetooth module it will go to the next level. So then we move on to the next module, which is the microcontroller board / the Bluetooth module. This is what has the algorithm and what's going to receive the data and process it through the algorithm, and then shoot it out to the dual hydraulic motors via voltage signals. 5 voltage signals are 5 voltage is the voltage signal that the motors are going to take in from the 7 to 12 volt range that the Bluetooth module and microcontroller is going to take in as inputs. The motors are dependent upon a 3 volt input, and those voltage values then move the solar panel to capture the maximum efficiency at where the sun intensity is the greatest. So this information of the sun position is going to rotate the solar panels as well as the photoresistors stated before.
So this is basically hardware iteration number 1, which is the microcontroller. So we went with the AtMega 328P, which has 23 programmable I/O pins, and it's compatible with Arduino IDE for programming via the FTDI breakout board. And here's just the pin assignments there. So this is our first hardware design, because we wanted to first get the microcontroller done, so that, because it's pretty much the brains of everything that's going to be happening with our project. So we wanted to get that done first. We had a few failed iterations in this, but this is the final product right here after a few adjustments were made. And then the picture to the left there is just it's iteration number 2, which is just the 2 motors working hand in hand, with one being the horizontal, one being the vertical motor. We just tested it out with just sent it a voltage signal, seeing if they're moving, able to move under the load that's being put onto them. And then the second picture there is the prototype that we have now, which is just like a smaller scale model of what we plan on building in the future. So it works on a series of photoresistors which serve as an analog input to the microcontroller, and then the microcontroller uses that information to send out a digital signal which is controlling the actual motors, that's the servo motors on the device, which in turn moves the panel itself.
Right, so for our software design, I included 2 snippets of our Arduino code that we've been using to program. We're using Arduino because it's the easiest to control our servo, because we're using servo motors. And for our smaller scale build, we felt like servo motors were the best option because we can easily control the angles of the motors we want and be able to use the outputs of the photoresistors and such and create them. And so basically, we defined the 2 servo motors and created high and low values for them so we can be able to set those. And we defined the pins for the photoresistors. And for our void loop, it's just our initial setup of our board. So when we start our program, it's going to set the motors to a starting value, and then the actual loop that we created is going to start to find the light. And we set the photoresistor values to analog values, so we're able to average them out and take the data from them. So in this other screenshot, we have just the main loop we have set up for averaging out the photoresistor values. So basically, several loops have been set up to check the values of various averages. So we check the averages of the top photoresistors, the bottom photoresistors, and we check those. And if one value is higher than the other, then we make changes based off of that. So they're able to accommodate for the position of the light, and yeah.
So for testing, we conducted several failed unit tests on our microcontroller because we could not get to be recognized by our computers, which is one thing we had to fix, which was all actual hardware connections with the wires that we had placed in the wrong positions. Another thing that we were able to do in the lab was, through the sensors that we had on top, we used actually an iPhone light to run it across different sections above and around the panel. And now it was able to read it properly through our horizontal motor, left and right. But we noticed that when coming up and over with the vertical motor, it would stop. And that's actually one of the things that we're going to be fixing for next semester. We actually changed to the bigger or more life-size panel that we're going to be able to use. So then we tested the code to make sure that everything compiled properly. Like going back to the connection to check the recognition, everything was okay.
So this is the schedule of the go no go milestone. So for the go no go milestone, we wanted to create a smaller scale model of our project just for testing out the codes and seeing if the design itself was good, and then testing out configuring all the minor things before we make it into a bigger model, just to get all those kind of calculations done first. And then here's just the schedule that we have set up. And then this is the demonstration where the light source in the room is a ceiling fan, the light there, and I press the reset button, and we see that it turns to face the light. So that's the original starting position when we hit the reset button. Then in this video, it's completely dark, and then I just used a flashlight to emulate the sun. Obviously, the sun's not going to be moving this fast, but it's just going to be simulating. So for right now, it tracks the sun pretty well, but there's still some minor adjustments that we have to make.
So for cost analysis, obviously a couple of things that we have to break down and stay organized. We just did integrated circuit, microcontroller, solar panel, 2 DC motors that we're going to use for the horizontal. And just different building materials, plastics, wood, anything that we need to actually put the physical board together. And parts that we're gonna have to invest for the future, there will be the actual Bluetooth module when it comes to connecting for our app. We're going to try to set this up and integrate with our phones. Building material for the final prototype, which is going to be a much larger panel. So it's going to be the larger base and stronger pieces to hold up that extra weight of the structure. Power meter and new motors, obviously because we're going to need more power for the heavier piece.
Okay, so future work, so for the winter semester, winter break, plan on making the small adjustments needed for the small scale model just to get everything like worked out, fixed. And then spring semester, plan on having the solar tracking algorithm completed and have the structure built for the final prototype. And then perform some unit tests on those, make sure those are working properly, and then finally like combine them both into one, make sure that's working properly, and then perform any more unit integration, and then finally acceptance tests.
Code standards and constraints. So the major focus of our project is operation in smaller residential areas, which we had mentioned before, that image that we're going to try to average for the average person to bring down the unit cost. Our design comes from the constraint that comes along with smaller site areas. Code standards and laws from the state to state regarding solar energy. So each state has their own, when it comes to anything that results in building design or energy efficiency, has their own code that they have to follow. So New York has their own, and all the other states have their own, which are very specific. And ethics. There are not many ethical issues with our project due to its passive nature, but the main ethical issue that we must consider in this project includes the existing patents, which are on the project from how we said this was something that we took from a couple of years ago, that design, and kind of just getting off of that. So we have to take that into consideration, and we have to follow the IEEE code of ethics. That's what we're saying with the building code and everything else that applies. The code that applies the most to our project is the fifth one, which is to improve the understanding of the technology, its appropriate application, and potential consequences.
And here's just the references. Any questions?
Have you considered you have a free floating solar panel? It's not fixed to the roof, so it might be subject to wind disturbance. Have you considered how you would sort of stabilize it in case of wind, protect it in fact, in case of wind does?
Yeah, that goes more into like next semester when we're
Yeah.
building the structure for the final prototype.
Practical consideration.
Yeah, we're gonna be looking at different materials that are like more durable. Obviously, see if we can find some more something that's less like impacted by the wind, like one of the
You might have to stabilize the whole thing, you know,
Yeah.
separately brace it, so you can control it and then leave it where you want it to be.
yeah.
Also considered, because since we have our algorithm where we have the actual geographical location of the sun, we were thinking of implementing maybe like a weather database in our application as well. So maybe when we have the like live weather feed coming through, maybe we can kind of adjust the solar panel's angle based off of the wind direction. So like if there's going to be like heavy wind coming from like let's say the south or something, and it's going to be and the solar panel, for example, is facing this way, we'd like to adjust it so that maybe it doesn't completely destroy our structure as well. So in our algorithm, we'd like to implement that as well. So hopefully